So we are interested in building primitives P from Q, and we often do this in black box way, and they come in different formats, 50 shades of gray for them, and this has been very successful, and we have been able to build different primitives. You never get to practice your talk on the stage, so here it is. And one central question driving this has been building key agreement from one-way permutations. And Merkle came up with this Merkle puzzles, which was a solution to this, showing a quadratic gap between running the protocol and attacking it, which is a fine-grained key agreement protocol. So Impagliazzo and Rudich looked at this classical problem of showing that actually you cannot do better than this. And so they had this algorithm, which basically seeing the transcript, conditionally sampled an oracle and random coins for the adversary, and basically trying to compute the same key, and then ran Alice on this partially sampled oracle and random coins and got a key out, and then recorded all the new queries that Alice makes to this oracle and it said Q, trying to little by little to learn these queries. And I recorded them and the keys in the another list K, and then at the end output the majority of the key. So why does this work? So, so this is taken from a paper of Zwickau et al. And basically the argument is very simple, that suppose that no queries of B are discovered when I'm doing that. B is Bob, right? Suppose that no queries are discovered. Then I'm sampling two oracles which are completely consistent because they are consistent on the queries which were sampled in previous stages, and currently no query has been sampled. No query has been discovered. So I'm running Alice and Bob with respect to an oracle which is completely consistent. So with the perfect correctness of the key agreement protocol, I actually get to compute the key because the key agreement protocol is perfectly correct. But note that B makes at most n queries to its oracle. So this means that in at least n plus 1 rounds, I'm going to compute the correct key. Right? So this means that if I take a majority, I'm going to get the key correctly. And this takes complexity n times 2n plus 1 to compute the key. And I guess the rest of the talks will be kind of more complicated version of this argument. OK, so after this work, there was a systematic study by Luca and others to look at the notion of fully black box constructions, and they formalized this. And the one formalization, which was fully black box construction, was that there exists a polynomial time construction such that for all primitives f that are implementing my primitive, then the construction with oracle access to f implements the primitive that I want to build. And there was also the notion of security of the construction, which was formalized for fully black box constructions as the existence of a polynomial time reduction, such that for all f's that implement my primitive and for all adversary, if A with oracle access to f breaks my construction, then reduction with access to the adversary and f breaks f. And then you can try to swap the order of quantifiers and add P to various quantifiers, and you will get all these different shades of black boxness. And RTV et al. Studied these notions, and they defined a number of different notions and studied relations among these notions of reducibility. And then Chris et al., Mark Fischlin, and Paul Becher from Darmstadt, they studied these even more systematically, looking at all possible combinations that you can have. But they also looked at two other aspects of these reductions, namely the dependency of these reductions on, for example, the advantage of the adversary. So sometimes in a reduction, we need that the reduction knows the advantage of the adversary. So they studied what is the effect of this on black box reductions. So for example, they showed that Goldreich 11 hardcore bits need to inherently rely on this advantage of the adversary. They also looked at meta reductions and a few other things, so a systematic study. And this has been a successful trade, these black box reductions, and people have been After showing that one-way functions do not imply public key cryptography, people show that one-way functions don't imply collision-resistant hash functions. Then later, public key encryption does not imply identity-based encryption. And after that, DDH does not imply IBE, and et cetera. And today, with respect to these classical black boxes, we are going to see impossibility of basing non-malleable codes for certain classes of tampering functions on certain distributionally hard problems. Then Chris et al. Are going to look at basing fine-grained one-way functions on average case hardness, even very strong forms of average case hardness, which amplify very well. And then kind of complementing this, Andrea is going to look at building fine-grained one-way functions from certain structured assumptions, fine-grained one-way functions on public key crypto. However, there are also non-black box techniques in crypto. So we have zero-knowledge proofs, garbling, functional encryption, because these are all primitives that take circuits as input. So when they take circuits as input, they have some sort of a non-black boxness built into them. So kind of motivated by these, people then asked, can these non-black box construction actually help in, for example, getting public key encryption from one-way functions? Or are there natural tasks that escape the powers of I/O? Is there anything that we cannot do with I/O? Or does secret key functional encryption imply public key functional encryption? Or Mohammed, Sanjam, and Amir looked at the question of whether I/O can be based on predicate encryption or on fully homomorphic encryption, and what sort of functional encryption is sufficient to build obfuscation. And so they went on to augment this black box model. So they defined zero-knowledge, idealized zero-knowledge oracle for circuits that have random oracle gates. And this actually models the Neuro-Young construction for going from CPA to CPA security to CCA security, whereas previously there were evidence that this is not possible. So so-called shielding constructions did not give CCA security from CPA security. And then Asherov and Segev looked at obfuscation for circuits with random oracle gates. Yeah. This is a model which, for example, models this Sahai-Waters construction of various primitives from obfuscation. However, these constructions don't have oracles which are the primitive itself. So you get oracles which are random oracle gates. We don't have primitives which are obfuscation gates or zero-knowledge gates. A zero-knowledge proof for a circuit which has access to zero-knowledge oracles. So Sanjam, Mohammed, and Amir looked at this monolithic model for black box reductions, which models the self-feeding constructions which have oracle access to the construction itself. And these sort of constructions exist. For example, functional encryption for circuits which have the key generation or encryption algorithm for the functional encryption submitted to the key generation algorithm. So today we're going to, Mohammed is going to look at powers of garbling techniques in this monolithic model to see what can be done and cannot be done. For example, there was the result that you cannot build IBE from DDH. Then there was a construction that you can actually build this. So then the question arises whether this technique actually helps in building public key encryption from one-way functions. So we hear about that. And next, Naomi is going to talk about certain weakenings of obfuscation, try to understand the assumptions behind obfuscation in this monolithic or extended black box model. So with that, I'm going to give the clicker to you, and I hope that it works. So thank you.